Good morning, sir. Satyajit this side.
Yeah, good morning, Satyajit. How are you?
I am fine, sir. How are you?
I'm doing good. Thank you. Thank you.
So, shall we start at 10?
Yes, we can start at 10.
Okay, sir.
Good morning, everyone. On behalf of BIT Mr. Fraternity, I would like to extend a warm and hearty welcome to our workshop on research methodology. Organized by Birla Institute of Technology off campus Lalpur, Ranchi. It is a great pleasure to have amidst us our special guest, Dr. Raghunandan Singh Gupta. Sir will discuss discriminant analysis with us today. A special welcome to our director, Dr. Vandana Bhattacharjee ma'am, who has been kind enough to support our endeavor. A very warm welcome to our esteemed faculty members, other guests, and attendees present here. Our guest speaker, Dr. Raghunandan Sen Gupta, is a distinguished professor of Department of I and Me, IIT Kanpur, specifically in the area of sequential estimation, statistical and mathematical reliability theory, risk analysis, optimization techniques in finance, meta heuristics techniques, re- reliability based optimization, robust optimization. Sir, your presence with us today is a refulgence and a source of inspiration for all the students present here. Now I request Sir to take forward this session. Welcome, Sir.
Okay, good morning, everybody. Am I audible?
Yes, sir, you are audible.
Oh, great. And thanks to the director, BIT Mestra, to the institute, and Professor Satyajit, and all the esteemed faculty members at BIT Mestra for this invitation, and a very warm welcome to all the participants who are there. Now, having said that, this lecture is broken down into two parts about the two topics. So it's about 1.5 hours each. So whether I'll be able to do justice to this vast area, I'll try my level best. Obviously, all the things may not be covered, but at least it should motivate people who are interested to take up this topic and other things which have definitely been taught very well by other faculty members, and it will definitely open up in front of you different avenues, different concepts, different applications which you can apply accordingly. To motivate the first topic, and the first topic is about discriminant analysis. So I'll just give you few examples, discuss the general concepts, basics, and then try to solve the problem from different point of view. So there are definitely many solution methodologies. I may not be able to discuss all of them, for which I apologize because time constraint is definitely there. So consider the first example, that a pediatrician has with her the data related to height, age, gender of kids who are in the age group of 2 to 5, and she has that from the past, because she has been practicing for the last, say for example, 4 or 5 years. Now based on this information, any child can be categorized as either being obese, being of normal health, or being malnutritioned. And depending on that, she will advise the parents of these kids or the guardians of the kids to either change the diet, take care of their health, whether some sort of extra consultation is needed, so on and so forth. So that it's because that's her expertise. Now, when a new patient, which is a child, comes and visits that pediatrician, that lady doctor, now once the child comes, the lady doctor has to categorize that person under any of these three categories, whether the kid is obese, normal, or malnutrition. So obviously these three categories may be more, may be less. It can be only two categories also. It can be more than three also. So she has to use some simple concepts like maybe body mass index, maybe try to find out what is the child's nutrition content, food intake, what is the person's age, the kid's age, whether the child has any other problem. So she will do it definitely in a very sound and methodological way, being a doctor. But as a data scientist, data analyst, mathematician, person who has knowledge about mathematics, you can also use the data to classify the set of people whose data is already there into three classes as given here, and you can also put any one person coming or two-person coming depending on the different input you get for that child into any one of the categories. So you have some methodologies to work on that. Second example, consider that a musicologist is studying the composition written by composers, Western classical composers between the year 1750 to 1820 AD, which is termed in the Western classical literature in arts as the booming period for Western music. So the musicologist is aware that a classification of the composer in that period, that particular time, about 100 years, a little bit less, may be made depending what is the melody, what is the rhythm, what is the dynamics, how the song was composed, what is the background, what is the mood, uh, the timbre, and all these things. So there are different classification concepts in music also, as we have in our Indian classical music. So there are different ways. You know that it's classified as the morning raga, the evening raga, and so on and so forth. So when the musicologist is given a new piece of an unknown composer, he or she doesn't know, then depending on the characteristics of the musical piece, what are the notes and so on and so forth, how many notes are there, so he or she will classify that, and then would basically classify whether that person that composition belongs to either Haydn, Amadeus, Mozart, Beethoven, Bach, Chopin. Basically, depending on that, he or she can classify that. Consider the third example. A geologist is classifying rock depending on whether it's an igneous rock, sedimentary rock, or metamorphic rock. And there would be different physical properties, how hard it is, how brittle it is, what is the chemical composition, what is the texture, what is the permeability, what is the color. And suppose he or she has already done it, and then the person is doing more excavation in the area of in the Chota Nagpur in Bastar district somewhere, and the person finds a sample of rock and then is told to classify that sample depending on the characteristics which I have already mentioned. So in all these three examples, and we'll just consider examples of a very simple one, good mathematical technique. So there are obviously other mathematical techniques also. A very good mathematical technique is known as in the area of multivariate analysis, which is known as the discriminant analysis. Consider a fourth example also. So you are a credit risk analyst. You are working in a bank, maybe SBI, investment, or PNB, or for some foreign bank, or you are in the financial sector, and you're interested to discriminate, classify, or put in groups different types of companies depending on average turnover, whether they will go bankrupt, whether they're performing average, whether they're performing good, depending on the liability, assets, price of the stock, price to earning ratio, then depending on the working capital, and all these things. You'll take all these ratios into consideration. After having that, you will study the credentials of different new companies which are coming into the stock market, and then try to analyze them, what classification you can do for these new companies depending on the set of information of the same type, but the values may be different. Same time means you have already done some kind of classification, so you will get the data and then try to classify that. So here also you can use the concept of discriminant analysis. Now, in discriminant analysis, what you actually do? So basically, you separate, discriminate, or put into different groups. So in this, that's the first step. So in this first step, you describe a some rule, an algebraic rule, mathematical rule. You can also do graphical rule also, so that you are able to differentiate observations depending on the characteristics or objects. Like objects may be the rock, color, permeability, what is the permeability, how hard it is, or how brittle it is, texture, and so on and so forth. Observations means for the company, you will find out the price earning ratio, working capital, total working capital, what is the overall asset, liability, at what time, whether it has got long-term debts, short-term debts, so on and so forth. So you classify into different classes, groups, and each group has different characteristics, features. So those features can be either physical, they can be qualitative, they can be quantitative also. And it is basically based on the inherent observations of the objects done and the characteristics which you have studied. Once you do that, you basically allocate, classify, and have a rule such that the next job which is to come, you'll sort that out depending on that classification concept which you used. You'll classify that in the particular group where it is basically the closest with the set of the characteristics. So characteristics need not be one, it can be more than one also. And as I said, the groups can be more than one also, or two also. Now, in discriminant analysis, the method is appropriate when the dependent variable is categorical. Characteristics, some characteristics is there, or even if there is a characteristic you want to quantify it, it will basically go into a level of 0 to 5, 0 to 10, and you classify them. While the independent variables are all metric which can be measured, whether discrete or continuous for the independent variables, we are not commenting on that, so it can be utilized accordingly. Like if you want to classify that rock which you're saying as hard, so that is basically a categorical one. You categorize them, and the input can be about the hardness, permeability. For each you can definitely use different type of simple engineering tests or some physical test you can do. This method of discriminant analysis derives the variate that best distinguishes between the prior group. Prior group means the groups you have already had. So you want to basically check a set of characteristics or one characteristic based on which you are sure that your differentiation would be of the maximum value. So what I mean by maximum value and why I am saying that, I'll come to that very soon. So this multi criteria method or this discriminant analysis, it sets the variate weights. So better the variate information is in that characteristics, higher the weights you will put. Lower it is, lower weights you will put, because that higher the weights would basically portray that you are trying to get the maximum amount of information from that characteristics. Based on this, you are sure that the grouping classification would be of the maximum value, which means in indirectly you are saying that the error, if at all there is an error, if you think, and obviously there would be an error of misclassification would be minimized to the maximum possible extent. So in the discriminant analysis, so let me continue reading this last point in slide 18. So the discriminant analysis sets variate weights to maximize between group variance. So because the variability best measure is variance. So there are minimized, because if they are being classified in one group and there are, say for example, 10 different individuals in that group, so the group characteristic should be such that the individual observations in individual reading which you are taking would be as close as possible to each other, which means the general characteristics based on which you are trying to classify them or the general characteristics based on which you are trying to basically group them, that characteristics within that group would be, the variance would be as low as possible because they are cluttered together. And when I'm trying to basically compare between groups, they would be as far as possible. That means the variance would be as far as possible between the different groups. So inter would be as low as possible. Any difference, maybe difference of color, maybe difference of weight, maybe difference of variability, maybe difference of height. You can consider the example, say for example, the pediatrician problem you have,
Sir, your voice is not audible. Sir, your voice is not audible.
hello.
Sir, it's audible.
Is it audible?
Yes, sir, now it is audible.
Yeah, I don't know why it suddenly. Just give me 1 minute.
Okay, sir.
1 minute, please.
Okay, sir.
Just hold on. Just 1 minute.
Sure, sir, no issue.
Is it visible?
Yes, sir, it is visible.
Okay, wait.
सेशन जॉईन केलंय का जॉईन केलंय
Yeah, so if you are like finished your discussion, then can I start?
Yes, sir.
Okay. So in the multivariate discriminant analysis, you basically group them in order to, as I was saying, maximize the difference between groups, but inside groups you will try to minimize the difference. What the difference is, it can be anything. It can be difference of the mean, it can be difference of the mode, it can be difference of the variance, any combination, or on a convex combination of anything. Now this you have already seen, so I would not be going much into details of that. So generally in any hypothesis testing, and this concept is also used in many of the multivariate statistics, but in that case you will have multivariate values. But I'll start with the and discuss and keep the example limited to the simple case. So generally whenever you are doing a classification, they can be two type of errors. So consider mother nature is giving two different outputs, good or bad, red or blue, black or white, right or left, whatever it is. There's only two. And your action or the test or the study or the look or the feature selection, feature study, whatever you do, also is in two classifications. Again, same thing. It is red or black, blue, black or white, good or bad, right or left, whatever. So you are trying to basically classify it as per the information, and you will try to verify your fact with what is actually, that is what mother nature has that information. So you have basically two statements. One is the statement where it is H naught, which is the null hypothesis, which you can either prove or disprove. That's a different question. I'm not going to go into that. And there's an alternative hypothesis which can also be true or false. So H naught can be true, false. HA can be true and false. So H naught and HA basically combine and make the overall set of all observation or all actions results based on which you are trying to do your analysis. And your action can also be classified as H naught and HA. So if both of them agree, so you have no errors. So if you see the white boxes where H naught is, you reject that means you are indirectly accepting H naught, and mother nature is also saying H naught is true. So this is white box, that is the second row last value of the cell. And if you consider that HA is rejected, H naught is accepted, as well as mother nature also says H naught is true, then that is also correct. So there is no error. The actual problem occurs in these two pink boxes, which is basically known as type 1 and type 2 error. Why? I'll come to that. So where it's saying H naught is true by mother nature and you're rejecting and not accepting H naught, so that is type 1 error of or given by the value of alpha. And if HA is true, that means H naught is rejected and you're also rejecting H naught. So there you are going in the opposite direction in mother nature, then it's basically type 2 error, which is beta. So this diagrams look simple, but there are complications here. Complication means practically many things cannot be determined, and if you go to higher dimensions, the problem can get aggravated. So let me give you a very simple example. So consider that you are a banker in a big bank, like chief manager, senior manager, in a very big city, in a government bank. and that's a very prosperous city. Many people come for loans, education loan, housing loan, vehicle loan, business loan, farming loan, many things. So you are checking one of the loan, and they have asked for a business loan. Now you have a set of procedures as per the government, and you have decided that based on the set of procedures, based on the questionnaires which are there, each question has some points, whatever the number of questions, 10, 15, whatever it is. And out of 100, if the person scores 60 and above, the person gets that loan. And if the person scores less than 60, the person is denied the loan. Consider that point 60 is that green vertical line. And for simplicity, consider there are definitely many people applying for a loan. To divide that to category, people who are not going to default, who will pay back the loan, consider that their distribution is normally distributed. Now here we are taking simply the normal distribution, which is a simplistic assumption, I agree, but still we are considering that normally distributed, and that's given by the blue one. Why blue one? Because it is on the right, and an average score you will assign to those set of people who will definitely return that loan would definitely be greater than 60. So maybe it is 80 or 75, something like that. So hence the blue hashed line is onto the right hand side. So if you see the x-axis, it gives you the scoring rating. From the left, you go more to the left, you go, score decreases, more onto the right you go, the score increases. And obviously with the same logic, the set of persons who would default is given by the red distribution. So their average score, which is given by the red hashed line, it is on to the left, which means its score is less than 60. Now, interestingly, two areas are to be noted. The red hashed area, which is onto the right, if you look at the diagram, which is onto the right of the green vertical line, and the blue hashed area, which is onto the left of the green vertical line. What do they signify? The green hashed line the red hashed line signifies those sets of defaulters who are given the loan because their scoring has come out to be greater than 60. So that area, if I say it's a beta, that's a loss because that's a bad debt. People who take the loan never return the loan. So that's a bad loss. It's a loss for you, bad debt for you, for the bank. While the blue one is, you consider those set of people who would have given you back that loan, but they are denied the loan, whatever the reason is. So that would be an error of alpha. So alpha and beta can be exchanged, but I'm using that similar policy which we use in general statistical problem. So there alpha is basically the set of people who would have been given the loan, but they are denied the loan. So they are your business loss, opportunity cost loss. Now you think as a banker, like, I should reduce both of them. So you try to shift that green vertical line either to the right or the left. But very interestingly, you will see if you shift the green one onto the left, the value of beta will increase, but alpha will decrease. And if we shift onto the right, alpha will increase and beta will decrease. So technically, you wanted to decrease both of them, but both of them at the same time is not possible. So what would you do? You will basically, in mathematical sense, how you solve, that's a different question. But intuitively, what you will do is that you will try to basically find out the minimum area or minimum value of the sum of alpha plus beta, such that you place that green vertical line in such a position that the overall area of the blue hashed and the red hashed when added together would be minimum, because when you're trying to minimize both of them, it's not possible. Now, in case if the distributions are not normal, so obviously you are now going to more practicality. If you see this, it conveys the same idea. The same idea in the sense the two distributions are, one is looks like a big flat plateau, which is the light gray one, and one is the which is on the right, and the dark gray one which slowly falls as a straight line is onto the left. And the you classification, because this is a classification which you have done considering that score of 60, so you classify will give the loan, back loan, would not give back that loan. The classification point is the vertical line which you have. So you classify in one class, classify in other class. So the classes are known as pi 1, pi 2, which I said that person returns the loan and set of person don't return the loan. So those are two classifications. So if you see that, it is given by, as I mentioned, alpha and beta, which is basically the overall area which you have onto the right hand side. So if you visualize the diagram which is shown, the blue hashed and the red hashed are basically the overall area within that bound, within that value. So that is what is given by this equation. Probability 1, situation 1 given true, and another is probability 2 given situation 1 is true. Based on that, you'll try to find out the area, and that the overall task is basically to minimize both of them. As that is not possible, you minimize some of them. Now if you extend that idea and say, for example, have 3 categories, maybe if you visualize, you can have different zones. In one case it is alpha 1, alpha 2, alpha 3, where alpha 1, alpha 2, alpha 3 are the errors with respect to, say, for example, the classification category 1, then classification category 2, and there's a classification category 3. So based on that, you have the areas given as alpha 1, alpha 2, alpha 3. So if you try to minimize one, so obviously you will see the other two would increase, or at least one will increase. And if one can be kept 0, so obviously it goes back to the initial problem which you are now discussing, that there is only 2 errors. So trying the main crux of the matter is that you cannot decrease all of them at the same time. So here is initial some information which is needed for that distribution. So I've taken a simple example. I'm not going to do the problem in details with this, but I'll give you the background. So this is a synthetic data set about the geometric features of pollen grains. So there are 3,848 observations based on 5 variables. This is taken from 1986 data by David Coleman in the RCL lab at Princeton. So basically the biologists were studying. The first 3 phases are the length of the geometric features observed and for the sampled pollen grains. So they are of, obviously it's a 3-dimension one, so these dimensions are x, y, z. And the other features based on which the study was done, they are the botanical features which is being mentioned. Whether there is a ridge, there's a nub, there's a crack, what is the weight, what is the density, and what is the observation number. That actually is given in the last column. So there are 6 columns of 3848 observations. So actually last column is the observation number, and 1 to 5 are the actual variables. So I find out the overall values, the simple statistical values, expected values, standard deviation of the sample, standard deviation of the population, median, maximum, and the minimum values for density, ridge, nub, crack, and weight, which are the 5 variables, and they are given here. I plot them. So plots are not that important or interesting. I'll come to that. So this is a plot of density plot for all the data based on the density. This is the plot for the ridge, second characteristics. This is the plot of the nub, which is the third characteristics. For all the data points, 3848. This is the plot of crack for all the variables. And last you have the weight, which is the 5th characteristics for all the data points which you have. Now, what I do is that I find out the expected value, the standard deviation based on the Excel this simple calculation which can be done, and the standard deviation based on the population. So there are different methodologies which are there, and there are sound statistical information for that which can be checked from both. And there's an error in the density. So based on that, I try to find out, and that's specific to the expected value which I'm trying to find out. So for a sample size of 500, so now this 500 can be taken any randomly. So obviously, you have 3848 data points. It can be done in actually in the huge number of ways. So it would be 3848 C500, depending on that. So the expected values are given, standard deviations of the sample, population, and the error. So I now start increasing the sample size. From 500, it goes to 1000. There's a background noise. Somebody's microphone is on. So there's an expected value for 1000. I also get these four characteristics. Similarly, I do it for 1500, 2000. Then I go to 2500, and finally this value of 3000. So I'm increasing the sample size. So if you see very interestingly, the error of the values for both the mean, both the standard deviation, and any characteristics basically is decreasing. Now, obviously, if I try to utilize the central limit theorem, it will mean that as you keep increasing, you'll slowly approach the normal distribution, and central limit theorem takes care and solves all the concept wise that you can take normal distribution to be true and proceed accordingly. So this is for 3500, this is for 3848, and if you see, the errors keep decreasing for all the values. I've only taken one comparison value, which is the expected value, the mean. Now I draw the frequency bar plot. So obviously you'll see more size, more intervals, finer intervals I draw, finer it becomes to a normal distribution. So if I have those intervals of a very broader class, then obviously this information would not be coming out immediately. But here the data set is quite large, 3848, so hence we can take that. So we take values of about 1 unit for the intervals, and based on that we plot the frequency, and from that you can get the relative frequency, and from that you get the distribution based on the fact that sample size is large. This I do for the cumulative distribution, and it basically resembles. So first point obviously was that for the PDF it resembled a normal distribution. Now in this slide 34, it gives us more information about the resemblance of normal distribution for the case. Now I do it for the ridge plot. So here for all the variables, by the way, for all the variables which I do, I'm trying to do it separately. So obviously some of them would slowly turn out to be normal distribution for the higher values of sample. Some would definitely give the characteristics of the normal distribution central limit theorem to be true much faster, in the sense for a smaller sample size, because they are more nearer to normal. Here I do it for the plots for the ridge, and this diagrams which I am showing, because these fall must have been done because I was going through the topics which have been considered. So these ideas of how to check normality and all this thing must have been done by QQ plots and all this hypothesis testing earlier. So I'm trying to skip that. But you can do either diagrammatically or through simple tests and verify the fact. Now this is one which I gave for the density. It can be done for all the other four variables. This is a comparison the QQ plots. QQ plots is basically known as the quantile plots, which is done considering, and obviously why I'm considering normal distribution, because it can be proved that for as central limit theorem holds true, your normality would hold true. Based on that we proceeded. But if the question comes that if I want to if somebody asks that if I want to do it for the variance, which is the second moment, or if I want to do it for the higher moment, skewness, kurtosis, or maximum value, minimum value, whether normal distribution can be used, and the answer would be no. The mean value would basically have the characteristics that it would slowly resemble the normal distribution as fast as possible. And for the standard deviation, it will be one of the distribution which you definitely would have done in inference techniques is basically known as the chi-square distribution. So if I have done it for the variance, so rather than normal, so say for example I'm trying to find out the variance of the density data. So I'll have on the y-axis the variance of the density data. On the x-axis, it would not be normal distribution, but it will basically be the chi-square distribution. So based on that, I can do the QQ plots for those variables. Now I will solve a very simple problem in the two-dimensional case. So consider, and it can be definitely be extended for the three-dimension case. There's no problem, but as I said, I'm always mentioning that the fact is that normal distribution is true. That may be a very simplistic assumption, very strict in the sense that you are doing away with non-normality and many of the other practicalities, but it gives you good results and an idea that how is the values based on which you are trying to pass a decision, how correct they are, how reliable they are, how good is your answer. So Hemant Mehdi is measuring the surface finish of a crankshaft. He is either working, say for example, in Tata Motors in Jamshedpur or in Pune or in some other place, or he's working with, say for example, Steel Authority of India, where crankshafts are being produced, whichever it is. And depending on the quality of the surface finish, so you want to basically check how the surface finish is, whether they are cracks or not, whether every welding has been done properly, all the work has been done properly. Polishing means not when you polish from the concept of engineering. The polishing has been done, grinding has been done properly. So depending on the quality of the surface finish, the crankshafts can be either good or bad, because good means they pass the test, quality test, and if one of the quality tests is not agreed upon, you consider that crankshaft is considered as a bad or a failed one. So Hemant checks a sample of 85 and finds 10 of them are bad. Help him to formulate a 95% confidence. So now few important points. This sample size is 85. That means he had taken a sample size of 85. So if you consider in that example the pollen grains, so just the example, so it was actual sample size was 3484. So in that case, I could have taken more and more observations for that study, which I gave a hint, but here I am only taking 85. And he finds that 10 out of them are bad. So obviously 85 minus 10 are good. And you want to help that particular gentleman to formulate a 95% confidence interval. So this value of 95 is something to do with the alpha and beta value which I have already taken. So I'll tell you what it is here. Whether it's alpha or beta, I'll come to that. So Hemant is to formulate a 95% confidence interval and find out for him the lower and upper limits of the confidence level, based on which he will check if the next data comes, based on the sample size. Like maybe observation comes in one unit or the observation come in a group. So based on that, he will do the tests of the characteristics of the shaft and then classify that particular observation as good or bad depending on what the predetermined values were. Now this 95 is technically is given by 1 minus alpha, and beta doesn't come into the picture. Reason being, because you want to basically maximize the sum of alpha and beta, as I told you in that example. So in statistic parlance, to solve this problem, what you do is that you keep beta fixed and then try to find out for what value of beta of alpha you get that answer. That means, as I mentioned, you keep one fixed and basically try to minimize the other. So the one which is fixed is basically beta, and based on that you try to minimize the value of alpha. It can be done the other way around also. You will get the same answer, like keep alpha fixed and then try to minimize or maximize beta depending on what type of problem you are solving. So this is a simple problem you would have done in hypothesis testing. So you consider n as 85. Now it's a yes, go, bad, good, red, blue, black, white. So there is a binomial distribution. You convert it into a normal case. Why you can convert? Because the sample size 85 is quite large. So based on that, you find out the probability of good as 0.1177 and probability of bad being 0.8823. So based on that, you first solve the problem and find out what is the confidence interval which is given there. 1 minus alpha is given, or alpha is given, whatever it is. So this 1 minus alpha would be the level of significance, level of confidence. Now this is a simple example where you convert a binomial distribution into a normal distribution. So you use this concept of central limit theorem, find out its mean value, find out its variance based on the fact that that binomial distribution has been converted. And when you put in the inference technique, based on the tables you would have definitely done, the chi-square, the F table, the T table, normal distribution table, which are there in the back of any good statistic book. Based on that, you find out the values are here you're trying to find out the control limits, the values maximum minima. So technically, if you see here, any new value coming, it's an average value. Remember, any new value coming of that crankshaft, if you pay attention to the last two values, which is lower control limit and the upper control limit, if a value is greater than 0.1826, it goes into higher value, which is category 1. It falls in a category of between 0.0492 to 0.1826. It agrees to the fact, but based on the fact that your level of confidence is 95. That means you want to be sure that you meet your requirements 95 number of times out of the 100. If you do that testing 100 number of times on an average, and if the value, so that means it will fall into category 2. And if you want to find out if the value is 0.0492 less, it falls in category 3. Now this problem is why I'm saying category 1, 2, 3 is for the following reason. Category 2 is good because it meets the criteria, so it's good. Then somebody can ask that if it is good, so obviously we have considered that it's a bad one. So anything value greater than 0.1826 or less than 0.0492, both are bad. Yes, it is bad, but I am further classifying because this is a crankshaft, and if you consider it's just a rod sort of thing, and you want to fit it somewhere, either in the car, the tie rod, or you want to basically the steering wheel, whatever it is. If it is more then some rework can be done in order to decrease that length and fit it. But if it is less, so it is difficult to add on material and utilize it. So category 3 would definitely be discarded. Category 1 can be reworked on, and category 2 is basically where it already fits and meets the requirement. So consider this example. So there's an international electronics company. It wants to sell its newly launched LCD television in Bhopal, and the company collects the following data, which is related to monthly income and size of the apartment the respondents stay. The flat can be either owned or rented, and the company which is doing the survey thinks, depending on the monthly income as well as type of flats they have, there would be a particular type of people with a certain salary per month, and with whether they have a house of their own particular size, they are willing to buy. So the company thinks technically there can be four type of people. Number one, salary is more than what is the salary bound that the company has to decide, because if this LCD TV is, say for example, of cost of 45,000 or 55,000, so obviously they know from the past data what type of people buy that, what is the average salary. So salary is a fact, and also apartment is a fact, because if somebody has rented, so the probability or the chance that the person would move either, so has been studies, so the company would think that the person is on a transferable job, so the probability of him or her buying that expensive TV is less. If it is a flat which is owned, so the probability is much higher. So there would be technically four. High salary over that value, whatever the value, it may be 1,25,000 per month, or can be 2,75,000 per month, whatever it is. So over that value plus an apartment being owned, that sort of people have the highest probability to buy, and the lowest probability to buy would be people whose salary is less than that stipulated value which I just mentioned, plus the fact the person doesn't have his or her apartment. Any other two combinations, has a flat but low salary, or high salary doesn't have a flat, they would definitely be in between positions, such that the probability of buying or not buying would definitely be in between. So based on that, you can classify. So here it is given family income in rupees 1,000. So there are 12 samples. So in that case, you saw that it was 85 for Mr. Mehdi. Here it is 12 for people who have the flat. So the salary for this 12 are, I'll just read up one or two values. With 90,000 per month salary, the apartment he or she has is of 1,840 square feet. Or if you see the last data, with a salary of 1,11,000, the person has a flat which is the size of 2,000 square feet. Or for example, consider the person has a flat salary of 1,40,000 or 100. So in that case, and a flat size of square feet of 1,920. So based on that, the category is done. So obviously it is a two-dimensional one. You can basically plot that and find out where these sets of points are. So if it is a higher dimension, 3-dimension, you can at least visualize. For higher dimension, it will be difficult to visualize. There can be many characteristics. And these set of people have income given, but they are on a rented flat. So the values are, say for example, if I read, the first person has a salary of 1,05,000, and the flat size is 1960. Another value, say for example 96,000, flat size is 1840. The third value, say for example the last one is 93,000, flat size is 1480. Now if you were to do that, you could also have solved the problem separately as Mehdi, or else you want to combine. So the combination can be done in this way. So what you want to do, so you want to find out, and this metric can change from person to person. Why? I'll come to that. Obviously there are different metric or different rules based on which you will do the classification, but the metric can change, and I'll give you examples later on. So you can maximize the square of the difference between the sample means. Sample means that you add up. Say for example you are trying to find out all the averages of the salary. Find out the average salary for group 1 and find out the average of this the salaries for group 2. Group 1 have a flat, group 2 don't have a flat. Find out the difference and square it. And obviously it will be per unit of sample variance. So why per unit sample variance? Because mean value will give you higher the values, mean is good, higher values, and but they have to be compensated by the amount of variance you have. So this concept comes from, again, some concept which you would definitely have studied in basic statistics. They are known as the concept of unbiasedness and consistency. So these concept of unbiasedness and consistency are being utilized, and there are a lot of mathematical rigor in that. So I'm not going to go into that. So you consider unbiasedness and consistency based on which you classify. Other can be, so you may be thinking, why am I using square? The reason being very simple. If you see the variance formula is basically a square. If you recollect your basic, maybe because nowadays statistics is also taught in class 12, as I saw. Maybe if you follow that, if sample variance is square, so that's why you're taking the square. If you're taking standard deviation, then rather than taking the square of the difference, you could have only taken the difference of the means. But there's also other problem, and this problem you may have encountered in regression concept which have been discussed. You must have seen it. So generally, if you find out the difference, so they can be very high values, very low values, which cancel each other depending on how high it is or how low it is. So even for a huge data set, you can find out the difference between the values. Hello.
Yes, sir. Now you are audible.
Again, it vanished. Wait. Okay. Saptarshi, tell me till what time does this first part go?
Sir, by 11:30 you can over the first half from 10 to 11:30. Then, if you wish, you can make a break of 10 to 20 minutes. Then again we can start.
So the issue is that because is there any other sessions after the lunch for
Yes,
them
after yes
for
after
the
the lunch there
candidates?
is a session.
Pardon? Hello.
Yes, sir. After lunch there will be a session
So lunchtime is from when?
from 1 to 2.
Okay, what I will do is that I'll try to wrap up by 11:30. In case not, I'll take another 5 6 minutes more and then take a break of 5 minutes and then start again. Is it
Okay,
fine?
sir. Okay, sir. Okay.
Okay, so here you have to find out the errors. So if you have two classes, so the observations can be from class 1, class 2, they can be greater or less. And based on that, as I gave the example for either the banker or for the person for the multinational company or for the other companies like for Mr. Mehdi, you can have different types of error. Like for class 1, type 2, alpha, beta. For class, the other class also type 1, type 2, beta. So you want to basically minimize some combination. What you do would basically depend on what is your main idea, how you want to minimize or maximize. Now here is basically where I will go into a added concept where if you remember I mentioned there can be different rules, so I'll just discuss few of the rules. These rules can either be solved simply. If it is normal distribution, they are very simple to solve, very simple. If it is not normal, so obviously you have to use either some simulation runs, and obviously all different type of packages are there to help you. Now whenever you're taking a decision, as I said, if it is quadratic rule and you consider normal distribution to be true for the returns, based on that fact I am proceeding. Practicality in many of the cases may not hold true, but even if you consider normal distribution in practice is not true, but still you consider normal distribution and quadratic one, still you get good results. So that's why I'm discussing it. So they are known as the safety first principle. Maybe some concept would have been taught, it's there in economics also, but I'll just go through the very brief idea. So safety first principle, if you remember, I considered one of the rule was maximum. I'll try to give you the other rules based on some examples, means ideas with diagrammatic representation, so that would be much easier. So there are other different rules, so because for time constraints I'm not able to cover everything. So one rule is simply the probability trying to minimize. And why I'm discussing that rule? Because that has got a huge amount of statistical input here, and those statistical input everybody would have done. And another is basically the rule which is non-statistical in nature, but still it can be converted into the statistical concept. So there are names, I'm not going to mention that. So they are known as minimization the probability, maximization of a value RL. What is RL? I'll come that with a simple example. And for example concept, it can be drawn that RL value would change for different examples. And one is the maximization rule. So there can be different rules of maximization, minimization, max, min max, so on and so forth. So I'm going to skip all those things. Now consider this very simple distribution, and the diagram will come which should make things much clearer to you. So if returns or the distribution based on which you are doing a normally distributed, then consider these things. The average value, if you remember the average value for the example which we were considering, that value of that electronic company. So it has, say for example, it is rather than two population where N1 was 12 and N2 was also 12, it is taking three populations. It can be four also, as I said. Has a house, salary is less, salary is more, doesn't have a house. Third one being salary less, doesn't have a house, and the last one is high salary, has a house. So it can be extended accordingly. So for the three case, consider the average values are given at 10, 14, 17. I'm forgetting about the units. Forget about the units. And the standard deviation have to be found. As I remember, as I mentioned, that maximization of the difference of the squares, square of the difference, and then divided by the variances. So the standard deviations are given for all the three classes. N is different here, whatever the N is. 5, 4, 8. Now, if you see here, if you draw the distributions, they are easily illustrated because you know the mean value, you know the standard deviation. And if you have a value of, say, for example, 5, and what is 5 I'm going to consider here, I'll highlight that. I'll give a very simple example. Say, for example, you and I'll bring that context of this simple example back here. Say, for example, you are an investor, you have some money and you want to invest. And there are two options. Option one is go to the bank and invest such that you get 5% interest rate, whatever the interest rate, continuous compounding, simple compounding. So that is immaterial. And other is basically you can invest in any share, any mutual fund, anything, post office, Kisan Vikash Path, whatever it is. Now, when will you do it? If the bank gives a 5% interest rate, which is definitely higher than any other investment, you will definitely invest in the bank, because the general average return from any other source apart from the bank is less than 5%. So as you're getting more than 5%, you are getting 5% in from the bank, you will definitely invest there. But if the overall value from other sources are greater than 5%, you would not go to the bank. So yes, no go situation. And it can be replicated for other decisions also. So if you go to that 5%, 5% value, say for example, if the company thinks that the number of people, so this average value is basically salary, if you remember, or the house value. So if it thinks that for a value of a house, it has done the study, and if it thinks for the value of the house or the space of the house or the average salary of the person, if it is less than some certain value, then 5 which I have taken, then it doesn't make any sense for the company to sell that product, because it has seen from the past data for people with salary less than a certain value or who do not have a house, you have a smaller house, their propensity, the chance, the probability of those type of persons buying that particular type of television LCD is minimal. So hence, marketing or targeting the market to those sort of people would not give you any results, because you have to do a test marketing, do a pilot project, and then understand to which sets of people the product you can sell. Now, if you base that and find out, so no, these normal distributions have not been normalized, that standard normal deviate has not been found from them. So you can find out the standard normal deviate by doing that x minus mu by standard deviation, which you all know. If you do that, consider for two cases, there would be a third case which would be for the third exam, the value. Consider, because I didn't want to draw that because it was becoming cluttered. So if you concentrate here, the average values are R bar A, R bar B are given. It can be R bar C also given. And this RL value 5% will be below which you would not go is that vertical red line. Now what is interesting to note is that the values of the graph which is on to the left hand side of RL, if you're looking at the diagram at slide number 47, so those would probability or those overall area would mean if that area is 10%, it means that out of the 100 people, if you do, 10 would have an average salary less than that RL value and they would never buy. So it doesn't make sense for that company to do that test marketing there and make the rule. Now, what will you do? So you'll try to basically maximize the area onto the right. So you'll try to basically find out on the right for the red vertical line, higher the overall area, that is the overall cumulative distribution, higher would be the probability of that sale happening. Hence, you'll try to maximize that. That means that categorization, if you remember Mehdi's example, that categorization will give you the maximum value. So any group following coming there where the probability is higher, you'll immediately classify that and take a decision. Yes, I have to basically spend some money in order to do the test marketing. Now, from where this rule comes, as I said, if you basically convert that into a standard normal deviate, you can find it accordingly and do the studies. So this standard normal deviate, again I am mentioning, is that x minus mu by standard deviation would give you that answer. Now, even though for our example we have simplified our assumption considering only normal distribution, but very interestingly, these examples can be extended for other distributions also. Obviously, if you have the tables, you have the mathematical proofs, you can solve it accordingly. But for simple example, this I am saying, for simple examples types which you are going to use, we rest assured normal distribution can be simply taken if the sample size is large, and you can definitely use, as I said, this normal distribution, standard normal, chi-square, t distribution, z distribution, or f distribution, all can be utilized to solve whatever type of problems which you have with quite good results. Now, where does this rule come? So in statistics, I'm not going to go into this simple detailed proofs. It's not required because this is not a mathematics class. So these rules comes from, there are many inequalities which are there. So one inequality is a Markov inequality, Chebyshev's inequality, Chernov's inequality. Those are bounds. Bounds means greater than that, less than that, whether possible, not possible, you assign probabilities. So this Chebyshev's inequality gives you that idea that you can find out what is the bound of the probability based on which you can solve the problem. And given that, again I am saying, given the standard normal table, you will have that. So this the probabilities would be given, found out from your data, and you can solve the problem accordingly. So this bounds you find out, and these bounds are all given in the sense from the data also you can find out. So if you look at the last value, sigma square p by RL minus RP. So RL is that value which you have stipulated for yourself, and RP is the average value of that particular section of the household for those particular set of people. So R bar P, so say for example there are set of people who have salaries more than, say for example 1.5 lakhs, which you think they definitely can be targeted. So you will basically add up all the values which are greater than 1.5 lakhs, add them up and divide by the number of households who are there. So that will give you R bar P. And this corresponding sigma square would be that sigma square for that sample set. So if you have taken number of people with a salary of greater than 1.5, about 20 in number, so you will try to find out the variance of those 20 only, not for the others, because other characteristics would be classified in other groups. So if you compare this Chebyshev inequality, it gives you a similarity between the safety first principle, or I would rather go the other way around. Safety first principle will give you an idea about the and bring you closer to Chebyshev's inequality or the other inequality based on which you can utilize this concept. The other rules are you maximize this RL, and what it means is that if you go back to this graph, considering the blue and the green are already fixed, if you imagine if you are trying to push RL, that means you are trying to increase the area onto the left, which you will definitely not take, and decrease the overall probability which is on the right. That means you will be more and more willing to invest or categorize human beings who have higher average values such that your sales or your categorization probability is higher. So if you imagine that red line moves on to the right, the probability decreases on the right, but the chance of trying to classify a household who has much higher values onto the right is much better, in the sense that you are assured of basically doing a marketing there for that the product which I was discussing, such that the sales would be of much higher certainty, because at the end of the day you have to basically balance that. So that what I said verbally or qualitatively is basically subsumed here. You maximize RL subject to some probability, so that is not that important to visualize. So if you consider this probability, why I have brought the probability in the picture, because that will give you a nice pictorial idea. So if you consider probability of RP less than RL is some value alpha, and you put some alpha can be 0.05, 0.10, 0.025, whatever it is. So once you do that, convert that into a standard normal. Even if it is not normal distribution, you can still utilize some of the concepts. So consider that you convert it into a standard normal, and you have that probability of RP in the bracket which you have RP minus RP bar divided by sigma p, which is actually capital Z, less than equal to RL minus RP bar divided by sigma p, which is the small z. So small z values can be found out from the standard normal table. Based on that, you can find out either if alpha is not given or vice versa. So here alpha is given, so RP bar is found out, sigma is found out, and you can find out RL accordingly, or vice versa, whatever is required. So here is so if you push RL more onto, it's given by Z because I have converted into a standard normal deviate value. So if you push Z onto the right hand side, it will give you the same analysis as I just discussed verbally. Now what it means from a simple notion of decision. So whatever we discussed was mathematics, what it means from the decision. So if you consider very simple economics, you must have done utility, you must have done curves, consumer curves, and so on and so forth. Consider this, you are trying to find out the best frontier. Indifference curves, you must have done something. Consider this curve which gives you the best frontier. So higher you go, more vertical up, RP value increases, more you go on to the right, sigma p increases. So obviously you will always try to go on to the top left corner. So where the red line arrow basically points, because you are increasing return also and decreasing risk also. Any values opposite in direction of red, that straight arrow is not at all appreciated, not at all expected. So you take a value, whatever the blue curve which you have done, I may have done arbitrarily, but it will give you some idea. So if you consider that equation with a value of alpha and keep that RL fixed, so you want your sales to be higher and higher, so hence you change the value of RL. RL means that average level of income for those set of people. So if you increase, keeping alpha fixed, you will just see it as a straight line, just simple class 10 mathematics. It's a straight line, it just moves parallelly. So increasing RL, it will move parallelly because alpha values and everything is fixed, and the point where it leaves that curve, that P star, where it is tangent, that will give you the best value where the categorization can be done in the best possible manner, reducing your error. Now, if I talk about the error, that error point was basically where I discussed alpha and beta. So you are trying to basically minimize the sum of alpha and beta. And you may be thinking, why I'm only considering that alpha value? Because I've already said, if you remember during the discussion, solving the problem can be done in two ways. Either keep beta fixed and then decrease alpha, or vice versa. Keep alpha fixed and do all the problems with beta. So here you can keep simply beta fixed because that's the standard norm. Based on that, I am trying to basically give the pictorial one. So obviously changing beta also would not suffice, because then you will go back to the initial problem that you cannot minimize both of them at the same time. Now, the last one was basically trying to maximize RP. So maximize RP has a different visual picture. The picture is like this. If you go back to the initial diagram, yes, here RL is fixed, it's not changing. But the curves themselves, blue and green, are themselves shifting onto the right. So if they shift onto the right, the area onto the left of RL starts decreasing. That means you are either you are trying to basically achieve the task in two ways: shift RL onto the right, or shift the graphs onto the right such that the overall areas increase. So you are looking at the picture at two different points. One is trying to minimize the loss, another is trying to maximize the profit. So if you're trying to maximize the profit, it also means minimizing the loss, because profit and loss are of two different answers. So if you're going to the north direction, is basically you're going away from the south. Or maximum minimizing, I'm trying to basically do it in the same way. But the way you're trying to tackle is different, but the end result you're trying to achieve is same. So you want to maximize RP, average value, that value of that curves. So that is very interesting here, because here value of that RL is fixed, R is not changing, and the green curve you take is same. So if RL is fixed, what you do is that you move it counterclockwise. And the moment it leaves that value of the green curve, that tangent point would give you the best segregation based on which you can do that answer. So these can be solved very simply of classification using simple trigonometry, but remember, here I am taking the concept of normality to be true, which I am mentioning time and again, because normality, even though we consider very superficially, but normality not being true obviously would have different ways of tracking the problem, but for all the practical purposes, normality can be taken as true and solve the problem. So here I have considered the problem. Here RL is given as 7% or 7 whatever value. There are 4 categories: 7, 10, 12, 15. Standard deviations are found out, and these values and standard deviation can be found out given the values, whatever. You can just simplify the average and the standard deviation. Based on that, when I categorize using the safety first rule, I find out the alpha for all the values, and I am considering, again I'm saying normality. I find out the values and then I categorize them, because I'm using the standard normal table. The small z values are found out to be minus 1 point, minus 0.17, minus 0.24, minus 0.35, minus 0.07. Based on that, I can categorize them as C is better than B, is better than A, is better than D. I will skip this because there's not much time for this first one. I'll skip this first
Sir, you are not audible.
Hello,
Yes.
Satrajit sir.
Yes, madam.
Sir, is meeting going on or shall we leave?
No. Sir will start the meeting at 11:45 a.m. It's a break.
Okay, okay,
Okay.
okay.
Thank you. Good morning, participants. This is Satyajit from BIT Lalpur. There is an announcement that due to some network problem with Dr. Raghunandan Sengupta sir, he may start at 12:30 p.m. and stretch it to 1:30 or quarter to 2. So can we prepone the lunch session? Means
Okay, sir.
1 से 2 जो लंच होता है वो अभी हम लोग प्रीपोन कर लेते हैं. सर का नेटवर्क प्रॉब्लम है थोड़ा सा. वो 12:30 से जैसे नेटवर्क आ जाएगा, जैसे नेटवर्क आ जाएगा वो स्टार्ट कर देंगे.
Okay, sir.
ओके, थैंक यू. Good afternoon, sir. Good afternoon, sir.
Good afternoon. Yes.
Shall we proceed?
Hello, we can start.
Okay.
So if everybody is there, I can start. Satyajit, you should tell me. Okay, I can start then.
Okay, sir. Yes, sir. We must start.
Okay. So sorry for this change in the timing because there was some net problem here. I apologize for that.
No, sir. It's not a big problem.
So we will consider the concept of cluster analysis. It's also a multivariate statistical method in which we form clusters or groups of similar characteristics objects or individuals using data information from individual objects. So if you remember in the first case of discriminant analysis, it was basically you have formed groups and then new group is a new observation or new subject or new object is coming. Then you classify based on the prior information you have already have. You check the new object's characteristics and classify that into the new group and to the groups which are already there, you put it in one group. So obviously the concept of error was there, which is important, which needs to be minimized. Here error concept is not there because no new group would be adding. You already have objects, you want to classify them depending on the characteristics into also new groups. So error concept is not there, mainly is that initial classification. This statistical method develops tools and methods. So given a data set which is in a matrix form, M cross N, where M are the individuals and N are the characteristics or dimensions, you want to basically classify them. So characteristics can be, objects can be, like say for example, there are different cars and the characteristics are color, what is the speed, mileage, maintenance cost, or safety concepts, luggage space, passenger space, what is the look. So both qualitative and quantity, based on that you classify. Another thing can be you are want to buy a house. So you want to buy a house, say for example in the city of uh, Calcutta or Bombay or Chennai, wherever it is, and the house should have different characteristics. Locality is important, how safe the house is, locality is, whether it's a gated community, whether you have friends there staying by, whether the hospital is nearby, how close is the school, how close is the bus stop, metro stop, whatever it is. Or you want to go to an MBA school and you try to analyze that MBA school characteristics by what is the rating, what is the placement potential, what type of quality of courses they teach, what is the faculty strength, what is the alumni feedback, how is the industry feedback, so on and so forth. So based on qualitative and quantity, we want to classify. So using cluster analysis, we try to find some similarity or pattern in the data. For example, classification of plants, animals, taxonomy, diseases, epidemiology, like trying to basically classify the different type of diseases, so on and so forth. So actually the work started in the area of anthropology, or you know that in biology we classify different genus, different type of species in different categories on the physical categories, so on and so forth. So the word basically comes from there. Or in chemistry, you consider your different type of chemicals, and you classify them. What is their solubility in water or in some other solvent can be used? What is their latent heat amount of heat retention? What is the melting point? And what is the corrosiveness properties? So you want to classify them. So these are a few of the authors which we have done work. Clustering analysis has been used very heavily in fields like anthropology, as I mentioned, agriculture, like you want to classify different type of plants, species, genus, different type of pulses, wheat, fruits. In marketing, say like different products you want to classify, club into different categories, different products from different companies. In finance, like different companies based on their price to earning ratio, their assets value, liability value, working capital, then turnover ratio, what is the liquidity risk, credit risk. In behavioral science, different type of human beings based on the characteristics. In engineering, it can be like different type of mechanical techniques which you use for different type of processes. So good references are given by Gordon, Hartingen, Andenberg, and so on and so forth. So I won't go into the details. Some other mathematical technique methods which are similar to classification, cluster analysis, pattern recognition. You check a pattern. Pattern is not only the how it looks like. Pattern would be many things, many characteristics. Numerical taxonomy, morphometrics, where you basically utilize different concepts of gene classifications and so on and so forth. So cluster analysis or CA is a tool of trying to build up groups, clusters from multivariate characteristics point of view. So CA aims to construct groups, again, as I said in the initial first part, based on homogeneous characteristics and heterogeneous characteristics. So groups with homogeneous characteristics are clubbed together, and groups with different characteristics are heterogeneous as far as apart, as diverse as they are, and they are clubbed in different groups. The groups of clusters should be as homogeneous as possible, and difference between among the various groups should be as large as possible, as I have already mentioned. So cluster analysis can be divided into two fundamental steps. First, you build the choice of proximity measure, how close they are. So what is the measure of proximity? Based on that, you classify, and once you check that, you basically check each pair of observation pairwise for similarity of the characteristics. A proxy or a measure is defined of the closeness, and based on that, they are basically clubbed as homogeneous, and they are classified as. If it is inside, you measure all the characteristics. It need not be unidimensional. It can be multi-dimensional also, like color, like maybe for the example about the geologist, it can be texture of the material, about the porosity, how quick it solves in water, then water retention property, how dry, fast it can be dry, maybe other mineral properties can be analyzed. So based on that, and the classification, if you don't want to put in other group, there would be other characteristics based on that which you do, how far they are. Like color difference is huge in the spectrum, so how would you consider? If porosity is different, how would you consider? Based on that, so classification here in the cluster analysis need not be in only two groups, it can be more than two groups also. So the four main steps of cluster analysis is: first, you check the feature selection and you extract the properties. Then you design a clustering algorithm. There are already existing different varieties of algorithms out there. Then once you do the classification, you check the cluster validation and how good or bad the characteristics in that cluster is, or that group is, and you then interpret the result. So no new observations are coming, existing are there, and you basically classify them into different groups. So what is all these 4 different stages? In feature selection, one chooses the distinguishing feature or features from a set of candidates, while on the other hand, in features or extracting stage, you utilize some transformation in case is needed to generate useful and novel features from the original one, and use that novel features as the classification metric or rule. Then the next step was clustering algorithms has to be designed. So you basically have to design a proximity measure. So that proximity measure is basically dealt with some correlation concept or some distance measure. I'm talking from a mathematical point of view. So distance measure need not be straight line measure. There can be other distance measure also. There can be distance measure between centroids, distance measure between median. There can be L2 norm. L2 norm is the Cartesian coordinate which we use. There would be distance measure based on the minimum, distance measure based on the maximum. There can be correlation coefficient, Spearman coefficient, and rank coefficient can be used. Different type of other distance like Hamming distance can be used. There are other measures like Minkowski measures, Canberra measure. So those are all utilized in different contexts. Like Hamming measures would be used more as a rule when you're classifying something to do with biological properties. While when you're trying to utilize this simple distance between the properties of the object, like distance between the average values, different average values for different class. So they are used for general characteristics of like height, weight, humidity, temperature. When you want to basically find out the maximum or the minimum, maybe you want to find out what is the maximum effect or maximum value in the Richter scale for the earthquake, or if you want to find out what is the effect of low temperatures in the Arctic, or if you want to find out the high temperature in the Sahara sub-Sahara region, there you will take the minimum or the maximum. Or when you want to find out, say for example in finance, the loss, so you will basically take the minimum value of the loss, or you want to find how good a company is doing, you'll take the maximum profit. So it's not always mean, it can be maximum, minima, in some other case can be mode is basically maximum, it can be median. So depending on that, the measures, one constructs a clustering criteria function so that the clustering algorithm can be then be utilized. The main focus of the clustering algorithm is to cluster objects into groups based on some predefined criteria. So there can be more than one criteria also. So you have to basically analyze one at a time and take the collective decision based on that. So say for example, you want to take the distance measure should be less than equal to, say for example, 3 meters, and consider no, not 3 meters, let me analyze between less than equal to 3 inch if you're trying to measure the height of individuals, and also you want to check whether the weight difference is plus minus 4 kgs. So if both these conditions are met, then you put that in category 1. So you have to check both of them, both have to be met, and it cannot be this or this. So based on that, you can design it accordingly. Then you have to validate the cluster. Effective validation standards and criteria are important to provide the degree of confidence you want to have in your clustering concepts and the algorithm is used. This is what is done in third stage, which is the cluster validation stage. And then you interpret the results. The ultimate goal of clustering analysis step is to provide the user with meaningful insights from the original data so that he or she can effectively understand what are the properties of that total group. So in clustering analysis, as I said, there are different type of distance measures. That distance measure is given by Dij. Very simply consider Dij is the distance between two different objects which you are trying to pick up. Like two different human individuals, the distance measure can be, say for example, the difference in the height. Heights are measured in centimeters. You want to find out the difference in, and the units is centimeters. It can be kgs also, as I said. Or if you are trying to find out the difference of temperature, low temperature of two places, it would be difference between the minimum. Or you want to find out the maximum rainfall between, say for example, Cherrapunji and other place in, say for example, in Assam. So that difference would also come. So find two observations, two at a time, with the smallest distance and put them in one cluster. Then once that is done, compute the distance matrix again between the n-1 clusters, because now initially you had started with n objects. So initially you will understand this m, the m number of objects, sorry, you will understand that they are, each individual is one cluster. So that means you are considering all of them are different, and then you start comparing. So first stage comparison, two are compared and put into one. So m decreases to m-1. So this should be m, sorry for that. Then you take the distance measure of this m-1 and take that particular cluster which has now two objects, you compare with all the rest. Then the third value will come there depending on the distance. So now you will basically reduce the total cluster size to n-2 and continue doing it in such a way that it would not be, all should not be in the group, but depending on the cluster, you will basically have, say for example, k number of clusters depending on the characteristics which you have basically put. Find two clusters again, next stage, with the smallest interclusters distance, because now it is reduced by 1, that's why it's m-1, and you will keep repeating till your criteria is met. So there are different distance calculation methods. Some is the minimum, as I told you, some is the maximum, as I have given an example. Some can be the average, weighted average, normal average. Some can be the median. Why the median? Because median would give you the value at which the overall probability is divided into half and half. Some can be interested to find out the centroid, and based on that centroid calculation you will do that. Some have different type of methods. One is the word method, and so on and so forth. So but we'll take the simple case of quadratic one, which is the distance measure, and solve the problem. It can be replicated for any other types of problems also. Other distance calculation measures are sum of square distance, which is the simple distance square we know. Can be mean absolute error, the distance the difference of the distance errors. You find out the mean of that absolute deviation or the distance. They can be mean squared error. That means you find out the average of that distance. Like if there are three objects, you find out the distance individually between them and find out the square, add them up and divide by 3. There is concept of Minkowski distance, Canberra distance, distance measure based on inequality measures. Inequality measures is that one which you have discussed, the Markov inequality, Chebyshev equality. The distance measure can be based on that also, because they would give you the upper bound, upper or lower bound depending on how you look at the problem. There can be other ideas of similarity or dissimilarity also. So some of these correlations are matching coefficients are Pearson, Spearman, we know in statistics. There is Jaccard coefficient, Tanimoto, which is based on plus minus the concepts of the values. There's sample matching coefficient, Russell and Rao coefficient. Dice coefficient is based on the fact what is the probability when you roll a die. So obviously we know the probability is half and half. It is an unbiased die, but depending on the experiment, you can have biased dies also, and the probability can change. They can be Kulzinski coefficient based on what type of measures you are trying to utilize. So these coefficients can depend on what type of distance measures you are using. So it can be L1 norm, L2 norm, L3 norm. So I'll come to these norms conceptually with very simple examples. So generally we know there's a concept of Euclidean distance, which is given by finding on the difference, squaring in them up, adding them up. So it is the distance between 2 points. If I find out the average, so that will become the mean average distance, which I just considered in the last to last slide. Now distance measures has different names. So one is the L1 norm, which is known as the Manhattan norm. So L1 norm is basically where you take the mod of the value. Why it is known as Manhattan norm? Because if you look at the pictorial picture of the streets of Manhattan, New York, so all the roads are exactly perpendicular to each other. So based on that, you consider the mod is basically the simple difference. So based on that, it's measure known as the Manhattan norm. There is other distance measure also by the famous statistician from India, Prasanta Chandra Mahalanobis, who founded ISI in Calcutta. So that's known as the Mahalanobis distance. That is more mainly used in the area of statistics and studying and different properties of agriculture for um, different type of grains and wheats, which have different type of yield values and all these things. So they are used there. Nowadays they are used in different spheres also, in finance, in marketing, so on and so forth. So Hamming distance is known that how many points are agreeing and are not agreeing. So that depends on the concept which I told is used quite popularly in the area of biological sciences. So L infinity norm is basically given by the max of these differences values, and based on that you have the LP norm, which is basically based on the concept that you are taking. The LP norm is basically the simple concept of the L square norm extended to the P dimension. So, but generally we'll follow the LP L square norm. Am I audible? Hello?
Yes, sir.
Yes,
Oh,
sir.
okay. Now this simple example with values. So you have in 2 dimension x values 2 minus 3 dimension 2 minus 5 20, and y as 12 15 0. So one point is 2 minus 12, second point is minus 5 15, third point is 20 0. Based on that, when I find out the L1 norm, that means I take the mod and add them up for 3 dimension, the value comes out to be 54. You can check up the second bullet point. When I find out the L2 norm, that means find out the difference of difference, square them up, and then find out the square root. The value comes out to be 31.55. And then the extreme case, I have the L infinity norm where I find out the max value between the differences. You can see it comes out to be 20, which means as you increase the norm value, the value slowly decreases. So here I have a graph, which means that as the norm number, which is in the x-axis, increases, the distance number values also decreases. So it's basically slowly plateaus down. If you see the I've done basically mark those points as the histogram, but if it can be done for huge number of points, it will become a smooth curve, slowly falling. So 2 dimension one I have drawn in this the blue, green, and red and the yellow. So what are these? I'll come to that one. So the red, blue, and yellow are based on the L1 norm, while green is based on the L2 norm. And if you see very interestingly, the length of red, blue, and yellow is same. So see, for example, you're moving from point A to point B. Point A is the lower bottommost highlighted the black circle, and the B point is basically on the top right hand corner, the black circle. So you want to basically travel from A to B. So if you use the L1 norm and you want to ensure L1 norm is followed, then you can basically have different paths of movement. So one is basically go straight up, then right, which is the red one. Another yellow one is that in the bottom one straight down, and then basically go one step up, go one step right, and then go straight up to reach that point. Similarly, if I take the blue one, it's a step function sort of thing. Go up, right, because your main aim to is to reach the point B. But very interestingly, the L2 norm is only 1 point. So that means if you have put at that formula, the difference square, then find out the square root. So there would be basically one path only. So the green line, which is the L2 norm, is unique shortest path, while the red, blue, yellow are of the same size but for different routes taken or ways taken. So this is why L2 norm has unique solution while L1 norm does not have any unique solution. So if you are using the L2 norm, you are bound to get only one answer if it is correct, and even if an other case when if you are using the L1 norm, even if it is correct, you can arrive at multiple values depending on how you have taken the distance measure. So what are the simple algorithms? I'm not going to go into the details. One is the basic key mean algorithm. The k-mean cluster algorithm works on the premise that the centroid of a group of objects best depict the characteristics of that group of the cluster. That means centroid has all the information based on which the characteristics can be found out. So why I'm saying the centroid, because that will be basically give an idea that in distribution which are not normal and they are skewed either on the right or the left, or the overall values are low, then you use the concept of the centroids, which is basically has some information about the distribution. That means there I will use, if there's skewed distribution, then median value will give you the best measure of the central tendency, the general characteristics. So the K clustering algorithm works on the premise that the centroids of the group of objects are best depict the characteristics of that particular group or cluster. So this is the basic k-mean algorithm. I am not going to go into the algorithm. I just gave the algorithm how it looks like, and anybody can basically understand that it's considering as a simple rule book step-by-step procedure. You can basically implement the basic k-mean algorithm, and nowadays with all the softwares which are there, you can definitely pick up the general the characteristics of the basic k algorithm, and inbuilt functions are also there. This is the bisecting k-mean algorithm. So here it's a simple extension of the basis of k-mean algorithm earlier. The idea is to obtain k clusters and split that set of points into those and into the clusters accordingly. So k clusters are already predefined, and then you pick up observations one at a time and put them into the respective groups depending on the characteristics. So this is a bisecting k-mean algorithm which can be implemented, but I am again saying it's a general rule how it works. So this is the basic agglomeration or agglomerative hierarchy clustering algorithm. So it's a hierarchy clustering algorithm whereby we start with points as individual clusters and each step merge those close pairs. So points slowly are subsumed under the clusters, and you decide how many clusters can be there, because more number of division, basically we would need more amount of number of divisions, more amount of detail analysis, and less number of clusters would mean that we need not be very rigorous. So you have to basically make a compromise accordingly. So this is the basic agglomerative hierarchy clustering algorithm. So you highlight and pick up the general concepts and try to implement that. So you have different hierarchies based on which you can prioritize them, prioritize the input values, so that will give you a better idea that how this cluster analysis algorithm do work. So this cluster analysis is just like a tree diagram sort of thing. So there can be used frequently and in ideas in hierarchical clustering. So that will give you a concept of some sort of tree, or consider you have a root, a big banyan tree, or a people tree, or a neem tree, and you consider you can visualize from the root different type of roots go. Root means different type of levels of the root of the plant goes, or the tree goes, and you want to basically find out that how this hierarchy can be modified in order to give the best set of information based on which you are working. So this word comes from two ancient Greek words, dendron. So I'm going to consider the dendron concept, which means a tree, and you want to basically draw it. So basic, and it's a mathematical figure, so that will give you some idea that how dendron is given. So this is like the dendron. So left side is basically the highest level, and basically you go down onto the right depending on the level of the that node is in the overall uh, flow process, or the idea of the clustering analysis. Okay, now before we solve one very simple problem, we have tried to analyze, because here decisions are made by individuals. So we would not always take the statistical concept in trying to basically find out the solution. We'll try to utilize both qualitative and quantitative ideas to model it. So we will very simply consider utility. Utility is basically the decision value which the person has. And if you remember, I did mention utility can both be the quadratic and not quadratic, but we'll consider the quadratic one, because I'm again mentioning the returns based on which you will take the decision would all be normal in nature, normal distribution in nature. The basic premise is based on the fact that selected alternatives should have the shortest distance from the positive part. So here now I want to basically formulate the problem in such a way. So I think I should describe the concept of positive ideal concept and negative ideal concept accordingly. So as you're doing the clusters, you are forming the clusters fine, but you will ask you a question that as you form the cluster and find out the centroid, so is there any particular best point combination which would have resulted a better answer? So that better answer will say, or the best one which can get will say that that's the positive ideal solution. Ideal in the sense, theoretically yes, but practically may not be possible to attain. Similarly, and obviously we want that clusters, or the characteristics of the clusters, to be as close as possible to the positive ideal solution. And alongside that, with that, you will have the negative ideal solution. That means you want to be, your group of, or the clusters needs to be as far as possible from the theoretical negative value. So this positive value and negative values are generally considered for comparison. Comparison in the sense you want to find out how good or bad your clustering concepts have been utilized. So consider that you have chosen the ideal solution and mark it as PIS. Say for example, I will find out how the PIS calculation can be done. Similarly, you choose the negative ideal solution and mark it as NIS, and I'll come to the details later on. So you need to find out the distance between the different type of alternatives based on the characteristics. And if you remember, if I mentioned that value of Dij, so here you want to find out as I mentioned, difference between the positive ideal solution and that individual value which you want to cluster. So maybe it is possible that the positive ideal solution is being utilized theoretically, but the difference between positive ideal solution and the on the objects based on the object based on which you are trying to do the clustering may be quite far apart. So obviously it means that trying to attain the positive ideal solution may not be possible. Similarly, you will try to find out the distance between the negative ideal solution and the object. So these are rules. So these rules can be changed accordingly. I am not going to why these rules can be changed. I am only taking the simplest example. So you need to find out the so-called ratio of the positive ideal solution and negative ideal solution, and based on the ratio, you'll basically try to put that in which cluster that particular object is. It may be possible that when you basically make the cluster, the characteristics may seem very close to the NIS, which is the no close to the PIS, which is the positive solution. But it should also mean that if it is closer, theoretically I'm saying, if it is closer to the PIS, it should always be furthest from NIS. Because in many of the cases, when you're doing this type of cluster analysis, your actual decision is as close as possible to the positive ideal solution. But on the other hand, it can be possible that the solution is also close to the negative solution, because based on the distance measure. So you have to make a compromise for that. Hello? Hello?
Yes, sir.
Yes, sir.
I'll just take a 2 minutes break. Just let me drink water and come back. Okay, just give me 2 minutes.
Sure, sir.
Okay, is the screen visible to all of you?
Yes, sir.
Okay. So as I was saying that you want your answer to be as close as possible to the positive one, but on the other hand, you also want your answer to be as far as away from the negative one, because that will be a win-win situation. Because it may happen you're close to the positive one and also you're close to the negative one, which means the characteristic division has not been done accurately. Another thing in between would be furthest from the as far as possible from the NIS, also far away from the PIS. That is also not advisable, because you want to be close to PIS. And the worst case would be which is as close as possible to the negative one and as far as possible to the positive one. So the two extremes are, one is closer to the PIS, away from the NIS. Other extreme is closer to the NIS, away from the PIS. and any other combinations would be in between. So you want to basically, based on what distance measure you want to basically calculate. Now the question would obviously come out that you will be interested to find ask is that which distance measure do I use, because that will have an implication, which you are right. So as I said, as I was discussing, this implication of distance measure will depend on type of data you are using. If you remember, I mentioned few examples trying to find out the maximum of the temperature, so you'll take the max distance. You're trying to find out the consider you're doing some study in the Thar desert, you're doing something in the Arctic Circle, it will be minimum. You're trying to find out the maximum effect of the rainfall, how floods have been affected by heavy rainfall. You will try to take the maximum rainfall which is happening, or you are trying to utilize some replacement of the genes, splicing of the genes. You will take the Hamming distance, or you are trying to do some find out the average or the height, so you will take the average, not the max min. So that will be L2 distance measure. So based on that, you will try to find out. If you want to say for example, find out the characteristics and do some studies about the stock market where correlation is important, you will use the correlation coefficient concept. So which you will use basically depend on the example, and that comes from either the information which you have or from your knowledge base. So as I said, your decision and my decision need not be the same, because you are trying to take both quantitative concept as well as some decision making which would have an implication from the personal view. So you will take the concept of utility and you want to maximize or minimize the utility. Utility is basically net value, net worth. Very simple. Positive it is, you will try to increase it. Negative it is, you will try to decrease it. And minimizing the utility function ensures, or the overall dispersion will ensure that you want to basically minimize the variance also. Variance means dispersion. If you remember in the first part of the talk, when we are doing the other topic, I did mention that in the ratio, one was basically taking the maximum of the square of the difference of the mean divided by the variance. So that their variance is basically some sort of loss or negative value or dispersion which you are trying to utilize here. Once you rank them based on the RIs, and then you can proceed step by step. This is one of the procedure. I'll come to a very simple example later on. Assume the distance decision matrix is this. And by the way, when I come to when I'm saying the example, I'll show you one detailed calculation of one data point, a big data point, and then that can be replicated for the other data points. So say for example, if you remember, you're trying to buy a house based on the characteristics, and you have a whole lot of information from different brokers. So we'll utilize one set of data for a house and classify it, and then it can be extended. There's no problems as such. And then we'll take that to extend that problem, we'll have many different houses with different characteristics and try to classify them in which category they will fall, and try to basically find out the distance. So once you find out the distance, you can classify them immediately. So assume a decision matrix. So what is the decision matrix? I'm going to come in detail. So that needs some explanation. So even though it may be a little bit vague to all of you, for the time being, consider that value is given, set is given. What is that? That will be context specific. So based on X, you find out the normalized weights. So here also a question. So a normalized weight which I'm writing is basically the value divided by the square root of the squares based on either the sum rows or the column rows. Now this normalization is also problem specific. So if you are using some finance data, you will try to utilize the logarithmic normalization. There are books which will give you ideas about. If you are using this problem where you want to find out the net worth, you will use this so-called normalization based on distances, which is square. So depending on different contexts which I mentioned, you will use the normalization accordingly. What is the data? Again, I am saying X will be discussed later on. So consider X is there, and remember the size of X is M cross N. That is very important. What is M? What is N? I'll discuss. So if you remember in the first half of the presentation also, I mentioned there was M and N. N is the number of objects, and N is the characteristics corresponding to each and every objects. Here also M in N and M are accordingly. So once you find out the normalization scale, normalization concept, you find out the normalized values which is given by the matrix R. So X and R are just a symbolic representation. You could have used A, B, C, D, whatever it is. So now consider this, I have values. Now these values, if you look, so let me concentrate on the first row. The first row basically gives, like say for example, I'll come to the house example later on. I'm buying a car, and the first row gives me the car one, which is the row one, and each element are the characteristics based on which I'm trying to analyze that car. So the first cell, which is 10 value, may give, say for example, what is the mileage, like per liter per gallon. The second one, say for example, is basically what is the overall safety features. So these have been just quantified. So there are other methods how you quantify that. Consider that as the safety features value 25. Then consider 25 is the resale value. So this first 25 and second 25 may not be of the same units. They are not of the same units, but the values are given just for ease of explanation. The third value, say for example, is the maintenance cost, and fourth value is, say for example, the luggage space. So for these 5 characteristics, I have characterized car 1. Similarly, row 2 gives me the characterization for car 2, then for car 3, third row, and then for car 4, fourth row. And the columns are, as I mentioned, are the characteristics or the attributes or the characteristics based on which you are trying to analyze. So once you normalize, this R matrix is given. So you see very interestingly, the R values are based on the first element 10 divided by the square root of all the squares of the first column. So now you could have done either the normalization along the row or along the column. But once you follow the principle, do not change the normalization in between. If it is along row, keep it along row for throughout the calculation. If it is along column, keep it fixed throughout the calculation. So here I do the normalization based on the column. So 10 divided by square root of, I'm talking about the first cell, 10 divided by the square root of square of first value 100, which is 100, square of second value, which is 25, square of third value, which is 225, and square of last value, which is 400. So I went through the first column. Similarly, when I come to the cell which is 25, initially in X, so it will be 25 divided by square root of 25 square, which is 625, plus 15 square, which is 225, plus 25 square, which is 625, plus 30 square, which is 900. So based on that, I have these values. I write these values. Now, very interestingly, you should note down. So just for your information, if you add up the values, so the values which I am saying, is the values which you have along any row or column where you have done the normalization. It should add up to 1. So check each column adds up to 1. So as it should be. So that means the normalization you're doing is specific to the row or column. So technically it means if you concentrate on the idea that each row is for the car, type of car, and the columns are respective to the characteristics. So if I consider the first column, and I'm only talking about till the two places of decimal. So the first value is 0.13, then 0.03, then 0.30, and then 0.53, which means the first characteristics would give me so-called importance of 53% to the fourth car, 30% to the third car, 3% to the second car, and 13% to the first car. Similarly, I will have the weights for all the characteristics. Now they will come the weights, and weights is very simply what is the level of importance you want to put on the values of the characteristics. So if you remember in the first half of the class, in the other concept, there was a concept there was a lot of things to cover, so I may have skipped that or discussed this very briefly. So there was something to do with the weights. Weights is basically a level of importance or relative importance. So if you consider this, there are n number of characteristics. So I put relevant weights of W1 to Wn where they add up to 1, which means what is the overall importance of the characteristics within themselves. The cars are not into the picture. So if I see the characteristics have the weights, if you see the principal diagonal, it is 20%, 10%, 15%, 25%, and 30%. So these are the weights which I have put. So once I have the weights, I multiply R and W. R is the normalized vector, W is the weights. So this comes out as the value, which I mention as the matrix V. So this is a combination of weights and the net value. So that matrix now comes out. So now basically the division of the positive distance, negative distance will start. So I club the most ideal solution as taking the maximum along the rows or along the columns depending on which direction you have initially done the normalization. So here, and remember here I is changing from 1 to m, which is the car number, car 1, 2, 3, 4, which is the row, and j changes from 1 to n, which is the characteristics number. So here 1, 2, 3, 4 along the columns, and this is along the rows. So here I take maximum along the I value. I is 1 to m. So and I put each value in its corresponding place, and I put a plus sign. So that's the maximum value. So if I do it, I also do a negative one. That means I take the minimum. So one end I am taking the maximum, one end I am taking the minimum. But always remember maximum, minimum I am doing along the I value. Depending on, again I am repeating, sorry if I am repeating too many times. So depending on how you have done the initial normalization. Once you do the maximum and the minimum, I'll come to all these things have been solved. I'll come to that. So once you found out the positive, negative, you find out the most positive ideal solution, theoretical one. So that will be given by the square. So now, very interestingly, you see a square root. So why have not I changed that distance? Because initially, if you remember, the normalization was done by the square root of the square values added up. So that's why I'm extending that. And if you remember, I did mention whichever normalization which you use, stick to that. So that's the reason. So I find out SI plus. Similarly, I'll find out the SI minus also. So this is the most negative ideal solution theoretically possible. For each value, I'll find out. Because here, if you find out, you are finding out for I is equal to 1, 2, 3, 4 till m. So you are trying to find out for each car in this case. Now you find out the ratio. So the ratio is basically the negative ideal solution divided by the sum of the negative positives. That means you want to find out some sort of efficiency. That means if you look at the ratio, it gives you the distance from the negative solution divided by the distance of both of them added together. That means how far or how close you are depending on that. Now consider the example. The same steps will be performed. Consider the problem. Okay, by the way, this problem which you are doing, if you see it, there are 4 choices, 4 houses, 4 objects. And what are the characteristics? There are 11 characteristics. So this 4 can be 20 also, no problem. And this 11 can be 22 also, no problem. I am just taking a small set so as that I can draw and then write the values and explain it here. Consider the problem is related to buying a house and an apartment among 4 choices or 4 localities in one city. Maybe you are in Bombay and you want to find out that places are Worli, Bandra, or Navi Mumbai, or some other place. And the characteristics are, and here I have taken city, but because I am considering different cities, but in that case, city won't be coming. The second bullet point to the last one, which is starting from price to resale condition, will come, but here the person is considering comparison of different cities' houses, which can also be done. So these are the city, price, loan availability, what is the location in that city, number of rooms in that apartment, what is the safety index of that house or apartment, how close or how far is the market, how close or far is the school, how close or far is the hospital, what are the facilities available, whether there's a gym, a small dispensary is there, whether there's a doctor inside, whether you have your friends who stay there, and so on and so forth. And what is the resale condition, whether if you have a transferable job, whether you can sell that house and move to other city. So those important facts you have considered. Now I consider some theoretical values based on 4 houses and 11 characteristics. So based on some scaling, depending, I do that. So what the points I have given here may be different for you. So if you remember, I mentioned it is both specific to the quantitative techniques as well as the personal level of feedback I have. So it may change, but the general idea of the quantity concept doesn't change. So I take the normalization as given, same normalization I have considered. So other normalizations can also be considered depending on the distance measured, if you remember. So this is the R value. And this R value, so those 2 blue ones have been highlighted in order to just highlight the calculation I have done, nothing else. They are not that significant. So 0.55964 have been calculated based on normalization as done, which is the element number R32 in the matrix R, capital R. And R48 value has also been highlighted, how the calculations have been done, which is 0.6471. Now the weights come. So the weights are basically specific to the person. So he or she thinks that there is 11.9%, 10.6, 11.5, 9, 11.3, so on and so forth till the last value of 5.8 for those attributes. So 11.9 is for the city, the first one, and 5.8 is for the resale condition. And you double check, all the values add up to 1. Now I find out V. So V values is basically multiplication of W into that A into R, normalized vector into W, sorry, R into W. And here I have done one value calculation, which is the blue one, which is the second row last value calculation, which is 2,11 calculation has been done. And how it has been done, I have just highlighted it for one case because it's difficult to highlight each and every value calculation. So now I have found out and I find out the max value. So the max value, which is interesting if you note down, so V1 plus is max of 0.0609, 0.0669, 0.0535, 0.0558. So if you look at here, I am going along the column because I have done the normalization along the column. I find on the maximum value here. So maximum value for 0.0609, 0.0669, 0.0535, 0.0558 comes out to be 0.0669. So this V1 plus is 0, is that value. Similarly, V2 plus is given by 0.6032. So similarly, I can do all the calculations. I have not written it here, by the way. I have written the values of V1 plus, and that's the vector. So that vector value is given if you see in the first bullet point here in slide number 143. So all the V plus values are given. Similarly, I find out the minimum values. Just for information, let me go to the matrix and note down the minimum value. So I find out the minimum value of the first column. That comes out to be 0.0535. So this is written here. And I similarly find out V minus. So once I have V minus, V plus, I find out the most positive solution and then most negative solution. So what I do is that Vij for each cell, I find out the difference within that with Vi plus, square it, add it up, and then find out the square root. Same concept of normalization which I have done. So once I do that, I find out Si plus, S2 plus, S3 plus, S4 plus. So now remember, these plus values are the most ideal solution for each and every house which I have considered based on that. Similarly, I find out most negative ideal solution. Again, difference square, but this difference is between that value of that cell and the most the negative ideal solution. So once I do that, I find out the ratios of C1 to C3. C1 to C3 gives me the value. So now what you see is where the analysis comes. So based on the range of the values, which can be predetermined and you can find out, I can cluster them. Say for example, I find out, I want to say that any value of the house, and remember, by the way, these values of CIs would be between 0 and 1. So if I say that values of 0.5 and below are one clusters, then house number 1, 2, okay, my apologies, the last one should be C4. So house number 1, 2, 3 are in one cluster of the same characteristics, while house number 4 is of the other cluster. So there are two clusters based on which I can do that. So I went a little bit fast, but I thought that ideas had been discussed. So one example should be helpful. So any queries if you have based on because that's on another thing. So you have your next class starting at 12 o'clock or 2 o'clock. So there is about 15 minutes. If you have any queries, I'm there to answer. You can just ask. So the house is open in the sense. Any questions you can definitely ask, both based on the first set of lectures as well as the second set of lectures. Hello, Shatrajit, are you there?
Yes, sir. Just a minute, sir.
Yes.
Hello. Am I
Hello.
on? Hello. Sir,
Yes.
sir,
Yes.
I have a query.
Yes.
Actually, I'm talking. I want to talk about the beta that we calculate for a particular security. Okay.
Huh?
Beta is the systematic risk.
Huh?
Sir, if the return of a particular security
Huh?
outperforms the market returns,
Hmm.
it is considered to be having higher beta.
Right.
At the same time, first I want to know what is the reason behind this, sir. And the second question is, when we include it in any portfolio,
Right.
and two securities are having negative correlation between them,
Right.
right? So it is good for portfolio risk. Okay. So this is a paradox kind of situation. At on one hand, we are having higher beta for two securities, say, and at the same time, they are having negative correlation with them, right? So how to create a trade-off between the beta and the uh, correlation, sir? That I want to know, sir.
Just one thing. I it was more of a from the discriminant analysis and cluster analysis, nothing from the point of view of finance.
Sir, this is a general question. As we talked about stock market and returns
Okay,
from
okay,
stock
okay,
market,
okay.
so I am relating it to that.
Okay, see, the concept of risk is not always standard deviation. So there are different measures of risk.
Okay,
So there are standard deviation, variance. Nowadays we use value at risk, conditional value at risk. So all of them have different flavors for the risk concept for the portfolio or the stock.
right,
But beta is basically used as a best measure to find out what is the relationship between the market and that particular portfolio.
right, sir.
So if you use beta and say, for example, standard deviation, and if the distribution, if you are trying to utilize is normal, then obviously the relationship which we will get between beta and the standard deviation would give you the same type of analysis, same type. But in the portfolio, when you're formulating, there are different types of stocks. Some are positive, some are negative, some have a negative correlation, positive correlation, some have zero correlation.
Right.
So trying to basically analyze the portfolio beta with respect to the market, you do not consider individual standard deviation. You only consider either beta or you consider only the portfolio standard deviation, nothing else. Because that will give you in the best possible manner the best way how you can analyze the risk. If you go into the individual risk, then obviously the idea of then diversification would not hold. At least the why you did the diversification would not make sense, because now you're going into the micro details, not analyzing the macro details. That all I can say.
Okay. Okay. Thank you very much, sir.